Hi, I'm Hoongyu Chung from Postec, and in this video I'll present our work on differentiable inverse rendering with interpretable basis BRDFs. Inverse rendering is the process of recovering same properties, such as geometry and materials, from images, given known camera and lighting conditions. However, this problem is fundamentally ill-posed due to limited live view angular sampling. To address this, previous works have employed basis BRDFs to exploit the spatial coherence of reflectance. This allows grouping of light view angular samples to compensate for the limited samples. However, when visualizing the corresponding weight maps, we observe that these basis BRDFs lack interpretability and their number is fixed. To enable accurate reflectance reconstruction in complex scenes, we propose interpretable inverse rendering with scalable basis BRDFs. Our method produces intuitive and precise reflectance reconstruction through specially separated weight maps. As input, we use a mobile camera equipped with a flash to capture multi-view flash images. This setup allows us to actively collect a sufficient set of live view angular samples. Our inverse rendering pipeline combines 2D Gaussian rendering with basis BRDFs. Each Gaussian stores geometric information along with weights over the basis BRDFs. We adopt a simplified Disney BRDF model for efficient reflectance modeling. We render an image and optimize the scene parameters by minimizing the loss between the synthesized image and the ground truth image. Assuming a collocate point light source, we compute the radiance of Gaussian by evaluating the BRDF using a linear combination of basis BRDFs and spatially varying weights. Then we render an image by alpha blending. To encourage sparsity in the basis weights, we apply a softmax function with a low temperature and introduce an entropy-based sparsity regularizer. This regularization loss reduces the entropy of both the Gaussian weights and the rendered weight maps. However, sparsity alone does not guarantee interpretability. To address this, we propose a basis control policy that dynamically adjusts the number of basis BRDFs. Let's consider a set of optimized basis BRDFs during the analysis by synthesis process. To determine whether two basis BRDFs are similar, we compute their radiometric difference. This is evaluated based on the angle between the half vector and surface normal, one of the most influential terms in reflectance. We also compute geometric difference using a point cloud formed by the centers of Gaussians where each basis BRDF dominates. To determine whether the basis BRDF is unnecessary, we examine the number of valid pixels in the rendered weight maps. If the radiometric difference is below a merge threshold and the geometric difference is minimal, we merge the corresponding basis BRDFs and their weights. If the number of valid pixels fall below a deletion threshold, we remove that basis BRDF entirely. Here are real-world results from our interpretable inverse rendering method. We reconstruct high-quality geometry and reflectance with interpretable basis BRDFs. This enables novel view relighting and intuitive reflectance editing. Using sparse weight maps, user can directly manipulate BRDF parameters such as base color, roughness, and metallic to achieve desired material appearances. In synthetic scenes, our method effectively reconstructs complex reflectance with spatially separated weights. Our reflectance editing enables realistic and detailed control over individual BRDF components through interpretable weight maps. Thank you for watching.